Okay, hello. Let us recall our previous discussions where we introduced uh, energy transferred by electromagnetic wave. In particular, we are interested in the rate, how much energy per unit time per unit area is transferred by electromagnetic wave. So in order to quantify this, we introduced one new parameter. Do we call it pointing vector? And the units for this pointing vector, when we're talking about magnitude, these are watts per square centimeter. So it means it actually is energy per unit time per unit area, but its direction shows us where the electromagnetic wave is traveling. And it is defined as a cross product of electric vector and magnetic vector at given moment of time. So we are dealing with something like instantaneous light intensity. So in given moment of time. So if we want to get more practical parameter, which is average light intensity or intensity of electromagnetic wave, then we need to integrate pointing vector over the period of electromagnetic wave. And then we operate instead of instantaneous values of electric and magnetic field, we operate with maximum values of electric and magnetic field. So who will recall me how we describe average pointing vector means intensity of electromagnetic wave in form of electric field. What is our equation there?
Electric field square divided by 2 mu naught multiplied by c.
Yes, but if we are talking about in average, so then we operate with maximum value, E maximum squared. So this here we see clearly that density, which is average pointing vector, is proportional to electric field maximum value in second column. So we will come back to this equation a little bit later. And obviously it is possible to describe it in form of magnetic. So also besides this fact that electromagnetic wave is transporting some energy, it also transporting certain linear momentum. And this linear momentum will, when electromagnetic wave interacts with some surface, either absorbing or reflecting, this will cause certain pressure, like exert some force, and force per square area will result in some pressure exerted on this surface. So how we define pressure exerted by electromagnetic wave on absorbing surface? Quite simple equation there.
S divided by c.
S divided by c, pointing vector divided by c. So obviously here we are operating with instantaneous value. If the surface is reflecting, then we just multiply it by 2 because linear momentum vector is changing its orientation on opposite. So now we make next step and switch our discussion to nature of light. So light, how would you give a definition of light in any, like from your understanding? What is light? So this projection of this image carried out by means of light, which is generated by the projector behind you. So what would you call light?
Electromagnetic
Mhm. To be more specific, because we have many electromagnetic waves, but light, specifically, we consider light what we actually can see. Because yes, it is electromagnetic wave, but it's part of the wide, like very broad spectrum of electromagnetic waves. And which kind of electromagnetic waves do you know, guys? So let's start from the shortest wavelengths and go to the longest.
Maybe like radiation, like gamma.
Gamma, correct. Then we have X-ray. Then we come to ultraviolet.
Infrared.
Great. You just skip the visible.
Visible.
Of course, that's the most important. All this, whatever manufacturers of TV or smartphones, the screens are advertising with hundreds of millions of colors and sub-colors and so on, and you just skip all of this. So we have UV visible, then near IR, then goes IR, because we kind of want to distinguish near IR and IR. Infrared means that is already a range where we can see with some special night vision equipment electromagnetic waves radiated by human bodies, so surface temperature is not so high. By the way, what's the temperature of human body under normal conditions? 36.6 degrees Celsius. Yes. So, as you see, it's not so hot, but irradiation happens somewhere in the range of 10 micrometers. So it's already infrared spectrum. And if you use certain equipment which is able to detect this wavelengths, convert it into some electrical signal, amplify, and then convert it in some display which can be observed by human, then we can see this radiation of human bodies on the background, either colder or hotter background. Okay, and what we have after? Microwaves, and then we have radio waves. Again, they can be, each of these can be distinguished in subsections, but in general, that is all electromagnetic wave spectrum. So light, which we understand as light, human beings, that's what we can see. Usually, we can see in the very narrow spectral range. Any ideas what is this spectral range?
10⁻⁷, like frequency.
Oh, if we are talking about wavelengths in nanometers. So we start to see something like 370, 80, and until 767 nanometers. So that is the spectral range of visible light, which can be detected by human eye. Of course, on average, under normal conditions, some people claim they can see amazing new colors after some drugs consumption, which could be possible. It's just the thing that the photopic curve of our perception of electromagnetic waves can be shifted because of some this psychotropic influence. But under normal conditions, that is the spectral range and combination of these different wavelengths. To be more specific, it is shown that combination of just three colors, red, green, and blue, uh, in different ratios, can provide us all possible colors and tones. So it's just all about the intensity of each of these color blended together. So that's why light is considered this spectral range. So if we are trying to give some definition of light, then we could come to this explanation, as you mentioned, electromagnetic wave in this specific narrow spectral range, 370, 770 nanometers, where human eye can detect it. However, if we look back into history, originally Newton was trying to give some explanations of nature of light, and you may know that his vision and understanding of light was this particle nature of light. So he considered that this is light is a flux of some particles which human eyes can actually detect and see. And based on this model, he could explain reflection, refraction of light, and so on. However, later, in early 1800s, Thomas Young revealed that light can show some very interesting phenomena as interference. Interference is a interaction of two coherent waves which interact with each other, and then we see some interference pattern of maxima or minima. So that is clear feature of wave nature of light. And later, so this was experimentally shown, and a bit later, by means of a well-known system of equations from Maxwell, it was shown that indeed, like on theoretical basis, was proven that light is actually electromagnetic wave, since it travels in free space with the same speed as predicted for electromagnetic waves. So at that time, it was almost clear that everything is known about light, and it's obvious that it's just electromagnetic wave, and nothing else is true. However, later, this already was like 1900, like 20th century, there was such effect, as maybe you heard about it, I believe you should, as external photoelectronic effect. So what actually stands behind this? If you have some, let's say, originally it was made on metal, we will consider a little bit later another feature of this effect when it's considered to be internal photoelectronic effect, and that happens in semiconductors. But originally, external one was shown on some metals which were irradiated by light, some, let's say, electromagnetic wave, and we could see some electrons going out from the metal surface, and we take to the free space to vacuum. So we place metal inside some vacuum chamber, shine light, and we create free electrons which kind of were ejected out from the surface of this metal. It was possible to measure its kinetic energy, what energy these electrons possess when they come out from the metal, and based on the reasonable assumption, it was expected that the kinetic energy of these free electrons which come out from the metal will increase with the increase of light intensity. Any suggestions why this was a reasonable suggestion? We already recalled today the expression for light intensity, and that was E maximum square over 2 mu naught C, correct? So now what do we see here? We have intensity is proportional to second power of electric field. So what we when we have a metal, we irradiate this metal with some electromagnetic wave. So inside metal, what do we have?
Atoms, electrons.
They are kind of ionized, so electrons are collective now. They are really moving in this network of positively charged atoms placed in the uh, crystalline lattice. So we have kind of free electrons within this periodic potential of the crystalline lattice. Then we shine light, or we direct some electromagnetic wave on the surface of this metal. What happens? Electromagnetic wave at some point penetrates into the volume of this metal. It usually happens like very thin layer next to the surface because electric field is screened by mobile electrons. But at this point, it's not so critical. It just penetrates into the material of this metal. And this electric field, as component of the electromagnetic field, interacts with free electrons. So if there is some electric field, there is a charged mobile electron, there will be some electric force exerted on this electron, and uh, we expect that this force will accelerate the electron. So electron will gain some speed, some energy because of interaction with changing electromagnetic wave, electric field as a component of electromagnetic wave, and that will increase its kinetic energy. So this kinetic energy part of it will be used to perform some work, which is considered to be work function. So it's work which has to be done to take out electron from the material and put it somewhere outside in free space. So then it's not connected anyway to the material. That's with zero potential. So some part of this energy will be gone for overdoing this work function. And the rest should be in the form of kinetic energy of free electron in vacuum, in free space. So expectation was that if we increase light intensity, and for that we just need to increase magnitude of this electric field, then acceleration will be higher. As a result, gain energy, kinetic energy of electrons will be higher. And eventually we will see that with increase of light intensity, kinetic energy of residual kinetic energy of free electrons, which we detect, will be also high. However, regardless of this fact, when light intensity was increasing, we could detect more electrons, like free electrons. However, all of them had only like fixed kinetic energy independent on light intensity. It was a really strange observation because looked like the increasing in electric field does not help to increase eventual kinetic energy of free electrons. And that was really counterintuitive. It was going against this model of electromagnetic nature of light. In order to explain this, Einstein actually he received his Nobel Prize for explaining the external photoelectronic effect, not for his famous equation uh, mc square or this general relativity series. So this Nobel Prize originated from this external photoelectronic effect, and it actually makes sense because Nobel Prize assumed to be, in most cases, granted, awarded um, by uh, for contributions which led to some broad practical application which changes human life. So for the external photoelectric effect, definitely at that time was much more practically applicable than this other series. Uh, so what he proposed, actually, he changed this paradigm of considering light as a magnetic wave only, but considered, okay, probably Newton's ideas was also right, and we can consider light as a flux of particles. We call them phonons. So phonon is a quantum of uh, electromagnetic or light energy, and energy of this particle is a function of wavelength or frequency of electromagnetic wave. So we can claim for some monochromatic light, means light which consists only from a single wavelength. We can write that it's a flux of photons with energy h times nu. H is Planck's constant, and nu is the frequency of electromagnetic wave. So we can maybe write it down so we have this. So energy of a single photon is h times nu. So how we can represent now the light intensity? So light intensity in this case can be represented as h nu, energy of a single photon, times some flux of photons, means number of photons per unit time per unit area. So then this will be light intensity. Because if flux gives us number of photons per unit time per unit area, then by multiplying with this energy of each photon, we get the actually energy transfer by this flux per unit time per unit area. So if we consider this model and forget about this electric field for this particular experiment of external photoelectronic effect, what we see here, that if we don't change the wavelengths, we keep this monochromatic light. H nu, H is a fundamental constant, nu is frequency of this monochromatic light. So this parameter doesn't change. So the energy which each photon is carrying will remain constant. We only increase light intensity. So previously we considered light intensity is increased by increasing of electric field magnitude. But here we will see that the mechanism of increasing light intensity when frequency is fixed is increasing the flux. So we will just increase, we will not increase the energy of photons, but just their number, which hit the surface of this metal sample per unit time per unit area. So that, in this case, really explains the behavior of photoelectronic effect. As I mentioned, against expectations, when we increase light intensity, we saw increase of number of free electrons, but we didn't see increase in their kinetic energy. Why? Because energy, the kinetic energy, will be defined by this photon energy, h nu, minus work function, which is required to take a kick out electron from the surface of the metal. Both in this case will be constant. H nu is constant because we don't change the frequency, and work function, it's a property of a given metal, so it doesn't change also. So we will end up with some fixed kinetic energy of these free electrons. However, increasing intensity means increasing the flux. So we just bombard the surface of metal with larger number of photons per unit area per unit time, and as a result we should kick out more electrons from the surface because these photons interact with the material and kick out these electrons. So with such model, when we call this like particle or corpuscular model of nature of light, this external photoelectric effect can be easily explained. And eventually we came to this conclusion that indeed light possesses a dual nature of electromagnetic wave and flux of photons. So wave and particle nature of light. And depending in the scope of which conditions and experiments we are considering light and light matter interaction, we need to deal either with electromagnetic nature or particle nature of light. So as I mentioned earlier, we can also consider a little bit the internal photoelectric effect. So first of all, I would like to underline that using this equation for expressing light intensity is quite practical and makes a lot of sense when we deal with absorption of light in material of some substances. So usually one of the most important field of interaction of light is interaction with semiconductors. And if we consider, for instance, some semiconductor sample, here is some light intensity, which is bombarding the surface of this semiconductor sample. And this light intensity is defined, let's call it I naught, that will be h nu f naught. So this is the monochromatic light with frequency nu, and we have this incident flux of photons f naught, which gives us number of photons per unit time, per unit area of this surface of semiconductor material. Then, when we interact with the surface, there will be some reflection. There is some reflection coefficient. So we can write that reflected light will be I naught times R. And another part of this photons will go inside the material. So they will travel inside the material of the semiconductor in this example. So we can consider intensity of light which goes into the semiconductor as just I, let's call it I prime times, and this will be equal to h nu times f prime. So that is light intensity of this light which was not reflected but went inside the material of the semiconductor. We assume that this light is absorbed by the material of semiconductor, and its intensity obviously will decrease as we travel deeper into this sample. So if it's our axis x, so if we go from 0, from the surface, deeper in the, increase this x and go deeper in the semiconductor, light intensity or flux in other terms will decrease. So there is an equation, it's called Lambert-Boger equation, which describes this dependence. So I prime as a function of x will be equal to I prime at x equals 0 times exponent minus alpha times x. So alpha is absorption coefficient. It's a unique property of the material which we consider in this sample, and its units will be 1 over meter or like 1 over centimeter usually measured. So if we multiply alpha by x, x is in centimeters, alpha is 1 over centimeters, so we have unitless number in the argument of the exponent, and that is the equation which allows us to determine how light intensity is reducing as it travels inside some material. It could be semiconductor or some dielectric material, doesn't doesn't matter so much. So now let us consider this internal photoelectric effect, which quite important. And when we put together atoms in crystalline lattice, they are packed very close to each other, and their electron orbitals overlap. When we pack them close, they start to overlap. Then we deal not with just individual atomic orbitals, but they are so close to each other that they start to form bands, energy bands. So a combination of different, of the same electronic orbitals of different atoms, they kind of start to group together and create energy bands. Those which define electronic and optical properties of materials are the two last energy bands, which are called valence band and conduction. In between them, there is so-called forbidden band, which is, in other words, band gap, where there are no energy levels. They cannot exist just because we don't have electronic orbitals which could create bands within this forbidden energy gap. So that's why energy structure of a semiconductor or dielectric will look like the following. So we have bottom of the conduction band, top of the valence band, and this is vacuum level. Vacuum level means that if charge carrier is located at vacuum level, it will be completely gone from the semiconductor material and will not have any interaction with it. So this gap is the band gap, forbidden energy. This forbidden energy will define the behavior of material. So if this forbidden energy is larger, let's put larger than 0 and less than about 3 electron volts, then we are talking about semiconductor. If it is less or equal to 0 electron volt means that conduction and valence bands actually overlap with each other, then it is metal. So we have semiconductor, metal, and in the case when Eg bigger, let's say we put bigger only, and about like 3 electron volts, then we are talking about dielectrics. So why is that? Because in order to conduct electricity for such material, let's say we're talking about semiconductor, we need to excite electron from valence band because valence band is occupied with electrons. We need to excite it and move it to the conduction band. In conduction band, this electron becomes free. It's so-called delocalized, and it can travel in the material if we apply some external electric field. So internal photoelectric effect is actually uh, this option. Because for this material, we can also have external photoelectric effect. If we provide enough energy, which will be sum of band gap plus this is so-called Xi. So there are two energy gaps here. One between the bottom of the conduction band to the Fermi, to the vacuum level, and plus Eg. So the sum of these energies will give us ionization potential. So if photon energy is equal to this ionization potential, we can kick electron from valence band up to vacuum level. It actually should be vacuum, not weak. Vacuum level. So then it will be classical external photoelectric effect because electron will be leaving the surface of this semiconductor material, will become free. This is classical external photoelectric effect. However, if photon energy, let's show it here, h mu is larger or equal to Eg and smaller than ionization potential, then we can transfer electron only from valence band to the conduction band. It also becomes kind of free. We can claim that by photoexcitation of this electron from valence band and moving it to conduction band, we also make it free, but it becomes free only within the bulk of this semiconductor sample. So it can travel all over the sample, but of course it doesn't have enough energy to go further, leave the surface of the material, and become free in vacuum. So that is the internal photoelectric effect, which technically allows us to delocalize electron within the crystalline lattice of the semiconductor and uh, create conditions when this photoexcited electron, which is not in thermal equilibrium with the material, to participate in the charge transfer of inside this semiconductor material if we apply external electric field. So the key difference between external photoelectric and internal photoelectric effects is actually the energy of this photon. So if this energy is larger than ionization potential, we observe external photoelectric effect and kinetic energy of free electrons in vacuum then will be HU minus ionization potential. However, if energy is not enough, but we have a semiconductor material with some band gap, then this electron will be transferred to conduction band where it becomes delocalized and can move within the crystal lattice, participate in charge transfer. So it changes conductivity of this material. It becomes more conductive, obviously, because we create more free charge carriers which can conduct electricity. And as you remember from our previous discussions, conductivity sigma is equal to what? Q times N times mu. N is concentration of charge carriers, and mu is mobility. So by shining light and exciting this electron to the conduction band, we increase concentration and amount of available charge carriers in the conduction band, for instance, which can participate in charge transfer. So it's so-called photo-induced conductivity in semiconductor material. So that is actually, in other words, internal photoelectric effect, in which happens when we just don't have enough energy for kicking this electron completely out from the semiconductor material. And of course, this is one of the key features which are used in optoelectronic and photovoltaic devices. So now let us summarize our discussion for today. We considered different points of view how light is, like was and currently is understood by scientists. We came to the conclusion that depending on conditions of the experiment, we need to consider either um, electromagnetic nature, so in order to describe uh, interference effects, diffraction effects of light, which could be shown. So in that case, obviously, we want to deal in this scope of the electromagnetic nature of light. However, when we deal with some so-called quantum effects, and one of them, the original effect was photoelectric, external photoelectric effect, according to Newton's model, we came back to this particle model of particle nature of light and represented intensity of light not proportional to electric field in second power, but uh, proportional to the flux of photons with given energy when we are talking about monochromatic light. So h nu times f. So in this case, it's possible to explain the behavior of photoelectric electrons, the kinetic energy when they leave the surface of the metal. Specifically, can explain the fact that with increase of light intensity, we observe increase of number of photoelectrons which are kicked out from the metal surface. But the kinetic energy in vacuum does not change. So that is because we increase number of photons, but energy of photon is remaining the constant. So with this, we also considered this Lambert's-Bourger equation, which explains how light intensity changes as it penetrates deeper in some material. So it's proportional to exponent in the power of minus alpha x. Alpha is absorption coefficient measured in units of 1 over centimeter, and that is the unique feature of the material which you can find in literature for different materials or can be experimentally measured. And also we highlighted the difference between external and internal photoelectric effects, which both play major role in the development of technology, material science, and electronics in general. The key difference is actually external photoelectric effects. We provide enough energy to kick out electron from the material, so it's larger energy than ionization potential for semiconductor when we consider as an example. And internal photoelectric effect, we delocalize electron by exciting it from valence band to the conduction band where it can move, and it creates photoconductivity of this sample, so it increases concentration of available charge carriers in the semiconductor, which can participate in charge transfer and conduct. So that, of course, increases specific electrical conductivity of this material. Okay, thank you very much for attention. We meet next time on Friday, and have a good evening.